Welcome back. Let's do one more example. Okay, so this is a new example. You can see we have a silicon chip and it's mounted on a ceramic base. This is actually very, very common. If you have a, let's say, laptop or your phone or your iPads, this is what's inside them. You have a silicon chip and it's mounted on a ceramic base. So what's going to happen is once your phone starts work, it's going to become really, really hot. And then what you're going to do is you're going to blow some air over it to cool it down. Otherwise, your phone won't work. So for example, if your iPhone is really, really hot, it will give you a message telling you it's too hot to work. You have to cool it down first. So this is what happens. Okay? All right. So what we have is we have W dot in is equal to negative 0.225 watts. What is this W dot in? Work going into my system, going into the silicon chip. What goes into the silicon chip? Electricity, right? If you want your phone to work or your laptop to work, what do you have to provide? Electricity. So this W dot in is electricity going into the silicon chip to make it work. And why is it a negative number? You can think of this same as before. The electricity, which is a kind of work, goes into your system. That means your system consumes this work. Consuming work means this work must be negative. Okay, and the next one, steady state. Steady state, that's good to know. That means no properties change over time. And then we know the temperature of the coolant is 20 Celsius, which is very reasonable because usually what you have is air. You just blow air over the hot foam to make it cool. And the ambient temperature of the air is usually 20 Celsius. Okay, and then again, if you have a coolant blowing over the silicon chip, what kind of heat transfer you have? It's called convection heat transfer again. And in order for you to calculate the Q dot from convection, the equation is given, same as last time. And H, the convection heat transfer coefficient, is given 150 watts per meter squared per Kelvin. What we want to find is temperature of the surface of the silicon chip in Celsius. And then from this temperature, we can say, oh, okay, it's below the requirement or it's too hot for the requirement. And this is what mechanical engineers do. Okay, so now let's take a look. What's your plan to look for T surface? Where does T surf show up? T surf shows up in this equation. So probably if I want to find T surf, I have to find everything else in this equation. If I can find everything else in this equation, I can find T surf easily. Okay, do we have everything else in this equation? So let's take a look. Let's copy down this equation. Okay, so I'm looking for temperature of the surface. I don't know this one. What about T coolant? It's given 20 Celsius, so that's good. I have that. What about H, convection heat transfer coefficient? It's given 150. What about A, surface area? What about A, surface area? Okay, actually the dimensions are given. It's a square. The length here is 5 millimeter. The depth here is also given 5 millimeter. Okay, so now can you find out the area where heat transfer happens? The equation here, A is the area where heat transfer happens. Okay, so where does heat transfer happen? Heat transfer happens on the top surface. the top surface of the silicon. So A is really easy to find. What is that? 5 millimeter by 5 millimeter. That's it. Okay. And you may ask, what about the size? What about the pore size? Do you have heat transfer happening there? Probably yes, but it's really, really small because the length here is really, really thin, right? It's very, very thin. So we can neglect the pore size. All right. In other words, I do have A. So now take a look at this equation. If I want to find out surface temperature, the only thing I need to find out is heat transfer rate, Q dot convection. If I can find Q dot, then I will be easily, I will be able to find T surface easily. Okay, so how do I look for Q dot heat transfer? What equation has Q dot in it? Obviously, first law, Q dot minus W dot equal to dE over dt. And again, before you apply this equation, you should check if your system is a closed system. Only when your system is a closed system can you use this equation. Okay, so what is my system? My system is the silicon chip. Is it a closed system? In other words, do you see mass transfer? I don't see any mass transfer. There's no inlet, there's no outlet, there's no mass going in, there's no mass coming out of the silicon chip, so it must be a closed system. So I can use this equation safely. Okay, next, same thing again. Steady state, steady state. We can do the same thing. Steady state, what's gonna happen? Steady state. So right hand side goes to 0. No properties change over time, and E, capital E, total energy, is a property. So right hand side goes to 0. And then the only thing I have is Q dot is equal to W dot. Okay, Q dot is the total heat transfer. How many heat transfers do we have? There's only one, which is Q dot convection. And then right hand side, W dot, how many W dots we have? There's only one, the electricity consumed by the silicon chip, which is W dot in. All right, and do we have W dot in? Yes, we do. W dot in is equal to negative 0.225 watts. So that means I have found Q dot convection. And now let's go back to this equation. Put a tick on top of Q dot convection, meaning I found it. And now take a look at this equation again. How many unknowns do we have left? There's only one, which is T surf. One equation with one unknown. I can easily find T surf. Okay. So what we do next is to rearrange this equation, move the one we're looking for T surf to the left hand side and everything else to the other side. So this equation becomes Q dot convection divided by negative HA and then multiplied by temperature of the coolant. Okay, so this step is just purely algebra. Okay, next what we do is to plug everything we have. Q dot convection we said is negative 0.225 watts divided by negative H. H is 150 and it's given in SI unit, so there's no need to convert. The next one, A. Remember, A is the area of the surface where heat transfer happens. In this case, A is the top surface of our silicon chip, which is 5 millimeter by 5 millimeter. We have to convert millimeter to meter, which is SI unit. It's 5 times 10 to negative 3 squared, 5 by 5. Okay, so that's the area. Plus temperature of the coolant, 20 Celsius. Make sure you use Kelvin because Kelvin is the SI unit. To convert from Celsius to Kelvin, you just simply add 273. Okay, so now finally our solution is 353. And because we used SI unit for everything in my right hand side, so my solution must also have a SI unit. The SI unit for temperature is Kelvin. Okay, because the question asks for temperature in Celsius, we convert it back to Celsius, 80 Celsius. Okay, Kelvin to Celsius, you can just simply subtract 273. Okay, so that's surface temperature of the silicon chip, 80 Celsius. From this temperature, then you can go further. You can say, oh, this temperature is too high for my design. I cannot let it happen. So that means this design is a failure. You have to do something to cool it down furthermore. Okay, so this is part of mechanical engineer's job to do thermal analysis and making sure everything is not too hot.